Recording.
Okay, my name is Joey Marranca. I sit in the back of the room, and I'm going to be doing my whole entire project on the 5 different interactions of photons on electrons. So why are we even talking about photons in the first place?
Why?
Well, photons essentially is going to be one of the major components to discovering about radiation. So objects including the sun or just even spacecraft all use radiation in different various forms. So one of the ones that we know today that we see all the time is your typical X-ray machine. This is going to file in a certain point that all the radiation could just flow through in order to just see different parts of the body underneath our skin. So it's going to penetrate through our skin. Other machines like a CAT scan have a 360 image by shooting different photons at different angles around the body in order to capture good pictures. One of the interesting ones is actually mobile devices such as your cell phone or computer or anything like that emit radio waves, but in a certain way so that they're in a form of non-ionizing radiation. What non-ionizing radiation is basically a photon hits an electron, but it doesn't cause it to be liberated from its state. So it's not going to fly off or anything, it's just going to stay in its same place. So to start out, a photon is basically a fundamental part of light. It has no mass, so mass does not involve it at all, and it behaves in 2 different ways. The first way that it behaves is by, at a higher frequency, it's going to behave more like a particle. And this is how I'm going to be explaining how it has the 5 interactions, because it acts with other particles, in this case electrons. The second way is going to be at lower frequencies. It just acts like a wave, kind of similar to radio waves, how they mostly get absorbed and they bounce off different objects and come back to the source. So, the first kind of interaction is going to be Compton scattering. So Compton scattering is basically when a photon, which is right here, is going to be shot at an electron, and once it's shot at an electron, it will actually deflect off the electron. So the photon will go in one way, and I showed that by the angle of theta, and then the electron will actually go in the another direction. So Compton scattering can be related just like if you have a big gymnastics ball and you kind of hit somebody in one direction and you fly in another direction. This would ultimately show you kind of what a photon will look like when it hits an electron. So we can use formulas to describe the actual angles, but Angela doesn't want us to know that crap, so we're not going to do that crap. But basically, this is ultimately showing how momentum is conserved, and in the way that this is going to be an elastic collision. So the next interaction is going to be coherent scattering. So coherent scattering is similar to Compton scattering, except that the electron is not going to move in this case. So the photon is going to be shot at an electron as shown here, and the electron is just going to move slightly. It's just going to oscillate a little bit, but not much because a magnetic field is holding it in place, and it doesn't have enough energy to be liberated from the entire environment. So basically, the photon is going to deflect off the electron at an angle, which we'll just call theta, and that's basically all that happens in coherent scattering. Okay, so the next interaction is going to be the photoelectric effect. You may have heard of this in some of your other classrooms, but never went over it. But basically, this is going to be when a photon hits a metallic surface. So this could be any kind of metal, whatever. Basically, the electron is trying to escape, but it can't until it's liberated. What this means is that the electron is held in its orbit, and it can't leave unless something of high energy releases it. So in this case, the photon needs to be, like here, the electron can only be liberated under certain circumstances. These certain circumstances would be if it has a high enough frequency. There's literally, there's a threshold where if the frequency is too low, it's not going to liberate it at all, and the photon will just bounce off and it won't do anything. However, if the circumstances are right and the frequency is high enough, the photon will shoot into the metallic surface and it will completely cease to exist once it hits this. In turn, the electron is going to deflect off of this metal surface and it's going to go away from it. And what I mean by these in the certain circumstances is that if you have a low frequency, but you shoot it at the highest intensity known to mankind, it still won't even have an effect on it because it needs to be that certain frequency. And basically, you could relate this in like the circuits that we do by having a battery, and you have a vacuum chamber with a gap, and you're going to have a metallic surface that's going to be on one side, on the negative side, and the positive side being the receiving side. And from there, basically, if you turn on the circuit and the voltage builds up until nothing can flow through, if you shoot a photon at that surface, it's going to in turn cause the electron to jump over to the other side, and it'll cause flowing through of the entire circuit. So the next kind of interaction is going to be pair production. So pair production basically is going to actually involve the creation of a positron and an electron. I'll get into these later, but so just like before, a photon is going to be shot near the nucleus instead of actually at an electron. So you can see right here, it's just going to be going kind of near to the nucleus. As soon as the photon goes near the nucleus, it disappears. And I know that seems a little weird, but literally there's not a whole lot of scientific evidence of what happens after that, but it basically, just to summarize it, it disappears. And once it disappears, it's actually going to create two particles. Or, I'm sorry, just one particle. It's going to create a positron, which is going to be right here, and it's going to deflect at an angle. And once it goes near the electron is going to come down in another direction. A positron is just basically going to be an antiparticle. It's going to be the exact same charge as an electron, just in the opposite pole. So it'll just be a positive charge. But this will basically sum up what pair production is going to be. So the last type of interaction of a photon is going to be photodisintegration. If you can't already tell, disintegration is in the term, so it's going to mean the destruction or the splitting apart of something. So a photon, like before, I don't have a diagram because it's kind of hard to show, but it's basically going to be shot into a nucleus. Instead of near it or just at an electron, it goes into the nucleus. And when this happens, basically the higher energy wave, but really it acts like a particle because from the behavior of a photon, it's going to be absorbed by the atomic nucleus. Once it's absorbed, if you've ever heard of the Bohr model, it's going to cause the electrons to all go into an excited state, and this is going to make the atom extremely unstable. And once the atom is in an extremely unstable state, it's immediately going to decay, and when this happens, it's going to split apart and it's going to emit some subatomic particles. And a good example of this, if you're into space stuff, it's going to be a supernova. What a supernova is it's going to be a star collapsing upon itself when it's at the end of its life, and it's going to in turn cause thousands and thousands of nuclear fission reactions to occur, and these are going to be due to photodisintegration of each atom. And this in turn is going to be what exactly photons are and how they behave in reactions.